All right, so as promised, we're back for some more. And now we're going to get into, let's say, two of the big reactions that we want to talk about from electrophilic aromatic substitution. And those two reactions are going to involve adding or making carbon-carbon bonds. So we're going to be taking an aromatic ring and we're going to be adding a alkyl group off of that ring. And so this is Friedel-Crafts Alkylation. Let's see if I can get my spelling right. Friedel-Crafts. So we're going to have Alkylation, and then we're going to have Friedel-Crafts Acylation. So Friedel-Crafts Alkylation and Installation. The mechanism for these are going to be the same, and it's going to be the same mechanism we've seen for the other EAS reactions that we've seen, the halogenation, the nitration, the sulfonation, those kind of things, okay? The difference is, so with alkylation, we're going to be adding an alkyl. With an acylation, we're going to be adding an acyl group, okay? And we're going to talk about what the difference is and why and how and that kind of stuff here, right? So, but the basic premise is this, okay? So we have Mr. Aromatic Ring, there it is, our good old buddy benzene. We're going to take some kind of alkyl group that is halogenated. Typically chlorine's kind of your go-to, although bromine works just fine also. And we're going to add some aluminum chloride to it. And what we will do is we will end up adding that R group. Ta-da! Right? You guys can see what's happening. This is going to react with the, right? The aluminum is going to react with the chlorine. It's going to generate the electrophile. The ring's going to attack the electrophile, and then we're going to end up reforming the ring. That's it. So I could stop the video here. All right, thank you for your time. Right, we've done a 2-minute video at this point. That's literally it. Okay. Now the limitation, and as you guys have probably been picking up at this point, is just what is the electrophile that gets generated and what consequences or what chemistry comes from the generated electrophile. Now, and here's the key, all right? So now I'm going to take the 2-minute video and make it a 3-minute video. We generate a carbocation, okay? All right, well, thank you for your time. Really, that's all I should have to say at this point, right? Because our carbocation and intermediates with carbocations, we've studied this so often, right? We studied this so often. And so every limitation that we have with a carbocation that you guys have learned about in all the previous weeks of organic chemistry are going to be present here again with this. It's not that these things magically disappear. A carbocation is a carbocation is a carbocation, okay? In general, they're always going to behave the same way. So what does that mean? That means that we can't, right, or we're going to have a really hard time forming a primary carbocation. We just aren't set up with those conditions here, okay? So we're not going to be able to generate a primary carbocation. When we do generate a cation, we're going to have to worry about shifts and rearrangements. We can't magically make that disappear, okay? So we're going to have to pay attention to that. So those are the two major things that we have to deal with, okay? So if you guys are with me so far, let's then, just take this and put it into action then, all right? So we'll start out with, kind of a generic example here. We'll do blue and green now. All right, there it is. We got an aromatic ring, we got isopropyl chloride, right? And we've got our aluminum chloride there, okay? Cool, so step 1, generate the electrophile. So this is gonna look very similar to what we've seen with our halogenation, right? We've got our, I'm kind of cheating here a bit, but I think you guys will understand, right? We've got the attack of the halogen to the aluminum. So we'll do this and we'll do that, right? So we end up generating this kind of intermediate here. Should look just the same as we did with halogenation. Now think about what happened, right? So is this chlorine really positive? No, right? Remember, formal charges are kind of a flag for us to pay attention to something, right? So, hey, look, there's something unusual going on about this chlorine here, okay? So remember that what this really does is weaken this bond here to the point that we can just go ahead and break that and generate our carbocation. Now we've got to pause and say, right? We start out with a secondary halogen here, and so we're going to end up generating a secondary carbocation. Stop, right? What does that immediately tell you guys? Okay, we're generating a secondary carbocation. It's okay-ish, it's not the greatest. This is going to be the slow step, the rate determining step, all this kind of stuff that comes with generating a carbocation. If what I just said was a giant word salad to you guys, stop right here, go back to OChem 1 stuff, and I don't want to go all the way back to OChem 1, right? I should know. Look, you remember, this stuff doesn't magically go away just because you don't want it to be around, right? You're going to have to understand this stuff. You're going to have to understand how carbocations work and shifts and rearrangements and all this kind of, please, okay? That's one of these core ideas out of OChem. So we're going to end up breaking this, generating a secondary carbocation and all that kind of stuff there, okay? So let's go ahead and do that. So finally here, we will do that, and we end up generating our fantastic electrophile right there. And then we have our AlCl4 minus that's just kind of hanging out over here. Okay, great. So there's step 1, generate the electrophile. We generated a carbocation. Pause. Can we shift? Can we rearrange? What's next door? How do we stabilize? All of this kind of, every time you guys generate a carbocation, you need to stop and go, is this a low stable position, right? You look next door, you look for resonance, you look for shifts, you look for rearrangements, all this kind of stuff that can happen every time you generate a carbocation. This isn't a way that we're kind of used to generating cations. It doesn't mean that this cation here is really all that different from any other one, okay? Once you get into the advanced, organic chemistry courses, we can talk about anion effects and all this other kind of stuff. Not here, okay? A great topic, an important topic, a useful topic, not what we care about at the moment though, okay? So now that we've generated our electrophile, let us go through and, okay? Let's do the next step, which is the ring attacks the electrophile. No big differences so far. Ring reaches out, grabs that right there. Okay. Oops, that should be in blue. Sorry about that. Maybe make that bond and that should be in green. All right. So far, so good. Okay, and then remember the key important thing, we generate a positive charge there, and I'm going to go ahead and, let me scroll down so I don't have to keep reaching up, right? There's the hydrogen that we're going to have to come back and pluck off to be able to reform our aromatic ring, okay? So, nothing different, right? This is all the same, right? This is nothing unusual should be happening here, okay? So there it is, ring attacks electrophile, we do our we generate this intermediate here with a positive charge and resonance, stabilization, blah, 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 all that kind of stuff, right? And so now the next step is going to come in and something's going to grab that hydrogen. So I'm just going to bring this down here, okay? All right, and so what's going to come back in? Well, it's the same thing like with our halogenation, right? So we're going to, what color did I have it? We had it in green. Let's do that then, right? So here is our aluminum anion that we generated before, right? So we take that bond between the aluminum and the chlorine, it generates HCl, and we regenerate our aromatic ring. So that's blue, this was in blue, this is green, green, and that's green. We have AlCl3 and HCl. Okay, cool. So there it is. Okay. It's catalytic. We regenerate the AlCl3. That way, when you do this reaction in lab, right? I might be giving away some secrets here, so sorry for the lab tech or whoever's working the labs for you guys. Right? They tell you to measure a certain amount of aluminum. It doesn't matter. You just put a little dollop of AlCl3 in there. It's this yellowish or whitish powder sometimes. Right, it's catalytic, so it really doesn't matter too much how much you put in there, right? It's going to go through and do the reaction. And you can monitor this reaction pretty easily because you kick off HCl, right? So you can monitor this, you put a little strip of pH paper over the top of your reaction, and as the HCl vapors come off of there, right, you're going to see the pH paper change, and when the paper stops changing, that's usually an indication that the reaction stopped or at least slowed down, right? So nice, simple, straightforward. I did this reaction countless times in my graduate work, it's still a very relevant reaction, okay? It's still a very relevant reaction. So it's one of these reactions that we actually use quite a bit in the lab. Some of these other things that we talk about, we don't really do it that way for a couple of reasons, but that's okay, right? But this is something that I did quite a bit. Okay, fantastic. All right, so now that we understand that, right, let's understand some of the limitations, although hopefully we already know some of our limitations. If I come in and I try to do this, let's say we're trying to add propyl chloride, okay? So we pause, we stop, we think, right? We identify that this is a Friedel-Crafts alkylation. How do you know? Well, we have an aromatic ring, we have AlCl3, we've got some kind of alkyl halide group in there, okay? So Friedel-Crafts alkylation, as soon as you think about that, aha, I know I have to generate a carbocation. If I generate a carbocation, all this other kind of stuff just comes tumbling out, right? So on paper, right, if we weren't thinking, if we weren't following along, right, we would say that this is our answer, where we simply, right, end up connecting our aromatic ring with wherever our halogen used to be, right? If you back it up to what we just did, that's all we really ended up doing, right? We just took the chlorine away, put the aromatic group in its place, okay? But that's not what happens, right? Of course, this isn't what's going to happen here because, right, I'm going to skip a step in here, right? Because that would imply that we end up generating that species, which then gets added to the ring, okay? You guys catch what I'm saying here, right? Because we end up plucking that chlorine away and we end up generating a positive charge in its place. But this is a primary carbocation. Is this going to happen? Not under these conditions, okay? Not under these conditions. Remember, carbocations only form if there's something that's stable, okay? So what's going to happen actually is going to be a rearrangement, okay, to where what we really end up forming is this here, okay? And then from there we get our product, which looks strikingly similar to what we just had on the previous example, okay? I'm not saying this reaction won't happen, I'm saying this won't get formed, okay? This reaction will happen. It's probably going to, well, not probably, it will be slower than the previous reaction that we just talked about to get to the exact same product right here, okay? So be careful about this. You cannot form primary carbocations. We're going to come back and we're going to make this happen, but we're going to have to do some shenanigans to get there, okay? So don't worry. But here it is, right? Carbocations, think about a rearrangement shift, primary is not going to happen, yada, 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 all that kind of stuff, okay? All right, so what else? Well, if we tried to get clever, right, and we tried to do a vinyl, this is a vinyl, right? So if we tried to do a vinyl acylation, alkylation, okay? So now we have a vinyl chloride. Remember, vinyl is when we're attached to a carbon that is in the double bond, okay? So we have a vinyl chloride. We can't generate that positive charge either, right? This is not something that we talked about how we can do, practically speaking, with generating carbocations, so it's not going to work here, right? So we might say that this would be our product, and that would be great if it, oops, one, two, three, oops, okay, sorry, I got a little bit excessive there with the carbons, right? So we might say that this is our product, but that's not going to happen, okay? Why is that? Well, we have to go back to stability of carbocations and the strength of bonds and all this kind of stuff that happens along the way, okay? But we cannot generate this here either, all right? This is alkylation, and so we have to have an alkyl halide. Now, the reason why I kind of hesitate to say that is because, of course, as I mentioned before, there's exceptions, and we can do this trick and that and add this. But remember, what we're talking about right now is we're learning still the foundation for organic chemistry, okay? What you will very quickly learn is that chemists are eternally adapting reactions. And so if you put this, special Lewis acid in with this alkyl halide, we can do this transformation under these conditions and all this kind of stuff. Friedel-Crafts alkylation is massive chemistry, right? There's a lot of it on there. For those of you guys who are interested in research and all this kind of stuff, if you guys know what SciFinder is, which I believe everybody on your campus should have free access to. So might be something that's useful for you guys to look up, but SciFinder, if you talk about Friedel-Crafts Alkylation, all this kind of stuff in there, thousands of literature papers dealing with it, right? So can I cover all thousands of that stuff? Nope. No, I certainly cannot, because I don't know it all either, right? And so remember, we're taking this back to its basics. And so what we're dealing with is we need an alkyl halide that can generate a stable carbocation, and then we can add that to our aromatic ring, okay? Fantastic. So let's move on to its brother then, I guess we could say, right, or its sibling, or its close relative, whatever you want to mention here, all right? So now we move on to acylation. Okay, what we're going to do here is take an aromatic ring. We're going to add an acyl halide into this, so let's just do this, okay? I guess I should have picked a different color, but yeah, sorry. You guys will get the idea here, right? We'll do a little bit of work and we'll get into it. And at the end of it, that is what we end up doing, okay? So first of all, what is an acyl halide? Well, an acyl halide is a subclass of carbonyl functional group, okay? So remember, anytime you see a carbon double bond to oxygen, that is a carbonyl group. Aldehydes, ketones, carboxylic acids, amides, lactones, esters. I'm forgetting one off the, probably at this point, that doesn't matter, right? Anhydrides, right? So those are all carbonyl groups. Acyl halides are a carbonyl functional group that has an alkyl on one end, right? And we have a halide attached to the carbonyl carbon. Now, pause. We're going to spend about 2 chapters talking about carbonyl chemistry, 2 or 3 even, right? We're going to spend a lot of time in carbonyl chemistry. That's the other main chunk of OChem 2, right? So if you're like, well, I've never heard of an acyl group before, or acyl halide, all that kind of stuff, well, here it is, and we will spend a lot more time with it coming up, okay? But that's what it is. So halogen, chlorine, bromine right here, attached to a carbonyl carbon, so double bond O and all that. And we end up doing the exact same thing that we've seen before. We basically put our aromatic group right where that chlorine is. Got it? Is the mechanism going to be any different? Well, let's see. We've got a chlorine, we've got a Lewis acid. They're going to bond. We're going to generate a carbocation, and we're going to end up adding that as our electrophile to the ring. So the answer is no, okay? The mechanism is going to be the same. And so then you should go, well, who cares then? Well, why do we do this, right? Okay, so let's go through and take a look at it, all right? So what is different? I think we have enough space here, right? Let's mechanism it up. Okay. First things first, we have to generate our electrophile. Let's get that going. So far, nothing different. The chlorine attaches, the chlorine attaches to the aluminum. I could stop here and, I could talk about the same thing about charges and bond strength, right? And so, what is maybe a little bit different here is we're going to end up breaking that carbon-chlorine bond, okay? And you're like, that's not that different. Well, what do we end up forming, okay? I'm going to draw this a little bit strange here, right, just for argument's sake, okay? And then we end up generating the AlCl4 also. Do you guys see this? Okay. This is our acylium, right? I believe that's what it's called. What do they call it in the book? Yeah, acylium, right? So this is our acylium ion. What flavor of carbocation is that, though? Well, right, we got a carbon that's bound to another carbon here, right? So we could call that a primary carbocation. Ooh, that's kind of unusual, right? But remember, it's not necessarily that primary carbocations are all that bad. They are less stable because of inductive effects or hyperconjugative effects, whatever you want to say, right? So if we can have some way of stabilizing that positive charge, that's the useful thing. And remember, if we want to stabilize something positive, we need to give it electrons. Well, I can't just pour a bucket of electrons into this, right? But if you take a look at it, this is our carbonyl carbon, right? That is our positive charge. And right next door, we've got an oxygen that's got lone pairs on there, okay? So really, what's going on is we can resonance stabilize this. I know I'm drawing this weird, and some of you guys might be cringing at it. Don't worry, I know. Okay? So what we end up doing is resonance stabilizing that positive charge. Now the geometry is not going to be like this, you know, whatever, right? That's a little bit unnecessary, I guess, at this point, but realize this is going to be a linear complex, okay? So we can stabilize that positive charge because of the carbonyl oxygen being there with its lone pair. We can donate, we can make that right there. There it is. That is the magic. The magic that we have here is that we can stabilize a carbocation. Wow. Okay? Now that's important because now we don't have to worry about shifts and rearrangements. Do you guys catch that? When you're doing Friedel-Crafts acylation, that carbocation is not really going to move because it's already at a very stable position, right? We can stabilize all that kind of stuff. That's the key part of it, okay? So Friedel-Crafts acylation, our electrophile, right, our carbocation is not going to shift. So now we can go through and do the rest of it. You guys can probably speed through this because you guys know exactly what's coming, right? Once we generate our electrophile, then the ring's going to attack it, okay? Nothing different here. So this is in red, this is blue, there's that, right? Fantastic. Come back, now we got to reform our carbocation, the same thing, excuse me, our aromatic ring. So the same thing is going to happen, right? Just like we saw before, the chlorine complex, right? The Cl, Al, Cl, whoops, Cl, Cl, okay. Boom and boom. All right. So we reform our aromatic ring. Blue, blue, red, red, blue, blue. We end up generating HCl and AlCl3 again, okay? So mechanistically, there's no real difference. The only difference is we end up generating a carbocation that is stabilized by that carbonyl oxygen. Got it? I don't want a carbonyl oxygen. I want an alkyl group. That's okay. We got you covered with this too, okay? So we've got a couple ways that we can actually get rid of that carbonyl oxygen, okay? So let's do a quick practical example then, okay? Let's say that I wanted to make that compound, okay? Let's say I wanted to make this compound here, okay? I look, I identify an aromatic ring, I know I add an alkyl group. Right now we've got two tools in our tool belt, acylation or Friedel-Crafts acylation or alkylation. We identify that we add at a primary carbon, right? So I can't go through alkylation, I have to go through acylation, okay? Which means I'm kind of working in reverse here, right? So I'll just do a double head, oof. I'll just kind of do a double, okay, I don't know what the heck's going on. All right, there it is, right? So working in reverse, I know I had to do an acylation and then convert it into this, okay? And so just following along, I know I can do those individual steps there, right? So let's do that one, and we'll do this step here too in purple, right? So let's come back in and fill in the red and the purple steps here, right? This, did you guys follow along with this? I start out with an aromatic ring. I have to add an alkyl group that is primary. I know I can't do that through alkylation, so I have to go through acylation first. Okay, so I'm just kind of working my way in reverse here. So let's now work our way forward. So let's do the first step in red. So I start out with my aromatic ring. In red, what I need to add is this. Got it. Following that. Okay. Let me just clean this up just a bit. Let me pause here for just a second, right? You guys should go through, draw the mechanism for this, okay? Why? I don't want to do the practice, okay? Let me pause and give you guys a quick pep talk here, or a quick, ideas from Dr. H. Look, the organic chemistry tends to be one of those courses that I get it, like, a lot of people struggle with, and it's funny, just in my personal life, when I talk to people, and like, oh, what do you do? I'm a professor. What do you teach? Chemistry. And I get these just like looks of utter shock and horror that I would waste my years teaching chemistry or something like that, right? Because a lot of people tend to, maybe not have the best of experience with chemistry, right? I happen to love it and I'm blessed with that, but what I mean is that I don't possess like a chemistry gene, right? It's not like I sprung from the womb and they said, oh, he's a chemist, right? There's nothing magical about me that helps me to really understand this. The only thing that I did, and the only benefit I have over maybe some of you who are watching this, is that I'm older, right? I've been practicing this for a lot longer. There is no magic to it though, right? It all comes down to practice. And so when I give you guys an example saying, maybe you guys should stop and work through that mechanism, actually do it. But it looks so easy and I can do it in my brain, Dr. H, you don't understand. Do it on paper, okay? I know you guys are intelligent. I'm not saying that because I'm required to, or I think you guys need a pep talk. I know you guys are smart. Otherwise, you wouldn't have made it this far, right, in your college careers, right? But stop, take a look, pause it here. Don't worry, I'll be back droning on as soon as you guys are done, right? And see if you guys can work through that mechanism, okay? Draw it out, practice it, make sure you understand it, okay? All right, so good. Now we've taken care of step number 1. Now we need to come back here in step number 2. What we're going to do is a Clemmensen reduction, right? 2 M's? Yeah, okay. So Clemmensen reduction. Okay, I know I've talked about this before. What do we mean by oxidation and reduction in organic chemistry? Mostly, all we're talking about is adding or removing bonds to oxygen. I need to remove bonds to oxygen, so I'm going to be reducing. Okay, so that's what we mean there. Okay. To do this, we need something called a zinc-mercury amalgam, right? So we basically have zinc in parentheses Hg. That's just kind of the symbolism that we use. We have some HCl, and we heat this up, okay? And when we do that, not a mechanism that we're going to learn, right? Because it kind of involves surface chemistry and some of this other stuff along the way, right? But anyway, if we do this Clemmensen reduction setup here, zinc, mercury with HCl and heat, we can chew off that carbonyl group, okay? And at the end of the day, then, what we are left with is me running out of room. Okay. Is that fantastic? Okay. Fantastic. Now we have a way of generating alkyl chains, right? But we have to go through this acylation intermediate, but then come back with a Clemmensen reduction. Now, later on, we're going to come in and learn about another method of doing this, because this Clemmensen reduction has some problems, okay? The problem is it's not very selective, okay? We can actually use this to reduce quite a few things, including nitros, okay? So HCl, not very selective. Zinc, not very selective, right? But that's fine. I'm not saying it's a bad reaction. I'm just saying we have to come back and be clever, okay? But there it is, all right? So there is our Friedel-Crafts Acylation and Alkylation. What we're going to get into next is the problem I've been avoiding all along. And the problem is, if you go back, every reaction I've started with, let me zoom in here, right? Every reaction I started out with has just been my buddy, good old plain benzene. And there's a reason for that. And the reason is, once we have something on the ring, we're gonna have to come back and pay attention to where the next thing goes, okay? So we'll talk about that more in the next video. I'll hopefully have that online for you guys within the next 2 days at the least. But this is the end of our Friedel-Crafts alkylation and acylation. Alrighty, I will see you guys next time.